Hello and welcome to this lecture. In this lecture, we'll see Bayes' theorem. Okay, it's a very nice and elegant and simple theorem. You already know the theorem by now. When I write it down, you'll see the proof is not needed. It's very simple, but it's extremely powerful. Quite often in problems, we'll use it in very simple ways, and it gives you a very nice, neat way to go from one conditional space to another conditional space through the original space. Okay, so that's one way of thinking about Bayes' theorem. And it's very convenient, and it shows up in problems all the time, and many intuitive questions that you will have in when studying something statistically, right? When you will have some conditions are very intuitive, and all those can be conveniently answered using Bayes' theorem. So let's get started. So I'm going to start with an example and show you the nature of the problem that you will have. Okay, so why is such a theorem very interesting and important? Let's go back to this toy example of two urns with colored marbles. We have seen this again and again. I guess this picture is going to haunt you for the rest of your life. This ugly little picture of two urns and a bunch of marbles inside them. So you're going to pick an urn at random, and you're going to pick a marble at random from the urn, right? So far we've been doing the calculation in one way, right? How did we do it? We said probability of urn 1 equals probability of urn 2 equals half. That was my B and B complement in some sense. And then given that I chose a particular urn, I was looking at probability of red and probability of blue and that conditioning, etc., etc. And we saw that that worked out quite easily as well. Now, what's interesting to some people is maybe there is someone who did not observe the first step. Okay, so they did not observe the first step, and they did not see which urn you picked the ball from. The only thing they are shown is the ball. Okay, so they see the end of the experiment in some sense. Okay, so this happens quite a bit. I mean, when you set up a complicated experiment, and we look at a complicated situation, you will only get to observe some things, and that may not be the most important root cause of the whole thing, and then a lot of things might happen and you will observe only one thing. Okay, so when you observe things like that, you may want to go in and figure out what could have happened inside, right? Internally what happened. You may or may not know, but at least you can try to probabilistically ask, statistically ask what could have happened on the inside. So the question down below is something like that. In this toy example, it seems really silly, but you will see quickly enough in realistic practical situations, these kind of questions are extremely crucial. Okay, so I might observe after the experiment is over, without seeing the first step in great detail. I might only observe that a red marble was selected, and I may be interested in finding out what is the probability that it came from urn 1. Okay, so this is a conditional probability. Okay, I want the conditional probability that the ball came from urn 1 given that I got a red ball. Okay, notice this experiment involves two steps. I pick an urn at random, and then I pick a ball, right? I only observe the color of the ball at the end, and then I ask the question, what's the probability of urn 1 given that I got a red ball? So this seems like a little complicated, right? It's not like a, maybe it is sort of like a law of total probability situation, but it seems different. The nature of the conditioning is different, right? Given that you're going to pick from urn 1, finding probability of the red ball is very easy. It's a very natural space, it's a uniform distribution. You quickly write down the answer. But this way, it's not clear what the distribution is. Probability of urn 1 given that you saw a red, it's not immediately clear at least, right? Same thing with blue, right? Urn 1 given blue, or urn 2 given red, urn 2 given blue, right? So you may be interested in questions like this. Okay, this is one such example. So here's a more interesting, maybe more realistic, practical sort of situation, and this question comes up all the time. I mean, we are going through a major flu epidemic, and these kind of questions are very critical in practice. Okay, so here's the question surrounding a flu test. Okay, so let's say you have a city where you think about 1% of the people have swine flu. Of course, you don't know who this 1% are. If you exactly know, you're done, right? So you have to have some statistical framework here, right? So you don't know who this 1% are, but you know that, or at least you have a belief that 1% of the people have swine flu. So someone says, I have devised a flu test. Okay, and what does the property that the person say the flu test has? Okay, if a person actually has swine flu, then with 95% chance that person will test positive in this test. Okay, that's their test. So it sounds pretty good, right? So about very high probability that if someone actually has swine flu, he'll be caught. Okay. And then look at the next one. In about 2% of the cases, very small number of the cases, even if the person does not have swine flu, that person will test positive. Okay. So, this is the test that somebody is giving you. Some pharmaceutical company or something has devised a test and they tell you this is the property. We have done some trials of this elsewhere, maybe in other cities and controlled circumstances, whatever, and we know that this is how the test behaves. Okay. Okay, you have a test, you have a city where you suspect about 1% of the people have swine flu. What do? You start testing, right? So, how do you test? Let's say you do this. Okay. So, notice the situation here. So, you pick a person randomly from the city, okay, and you test them. Okay. So, you have a test, you can pick a person, you pick a person randomly from the city and then you do the test and the test comes out positive. So, notice in this situation you never got to observe the first step, right? What is the first step in this experiment? The person contracted swine flu or not, right? You can never really observe that, right? So, they would have got swine flu through various mechanisms, maybe they traveled, maybe they went close to someone else. I mean, it's very hard to observe that. You can never really observe that. That's what I meant when I said in many experiments, you know that there is a two-step sort of process, but you can never ever get to observe the first step, okay? But the second step, you can get to observe. If you pick this person and then you do not know, you can never find out whether they actually have swine flu or not. So, that part is just a statistical number for you, 1%. You do not know exactly whether that is true or not. You have to rely on the test. So, you do the test, you know whether the test ended up positive or not. Okay. So, this is the sort of realistic scenario which mirrors the urn experiment, right, in some sense, the toy experiment of the urn. So, in this case again you see that probability of swine flu, that the person actually has swine flu, is 0.01. And probability that the person tests positive given they have swine flu is 0.95, and probability that they test positive given they do not have swine flu is 0.02. Okay. Now, the crucial question you are interested in clearly in practice is the reverse, isn't it? Probability that the person has swine flu given that they tested positive. Okay. And you want this number to be very, very large, isn't it? You want it to be 90+%, right? So, then you can be reasonably sure that yes, this is a good test, I can use this test successfully to go around and find the people who are interested, who are infected with swine flu, maybe, right. So, that seems like a interesting question to ask. Okay. So, here again you have a situation where you are interested in this reversing of the probability. Probability of positive given swine flu is easy for you, it is given to you, the company which comes and markets the test has to give this to you, but the reverse probability is not something that you have, isn't it? So, how do you do this problem? So, again two problems with the same flavor. So, let me just put it out abstractly for you. You have two events A, B, P of A, P of B are known, okay, let us say, alright. And then P of A given B and P of A given B complement are either known or easy to find. You can easily find this or you know this, okay. I want to find the reverse conditioning. I want to find probability of B given A. A given B is given to me, or I know it, A given B complement also is known to me. What about B given A? Can I find probability of B given A? Is there a way to move from these conditional spaces? Notice the conditioning on A is a different probability space, isn't it? It's a different conditional probability space. Conditioning on B is a different probability space. Are these probabilities related? Okay. So, if you think about it, they are related, and that relationship is exploited and specified as Bayes' theorem. Okay, and Bayes' theorem is stated as follows. It's easy enough to state. I've just drawn a picture here to highlight you what is going on. There's a sample space here, so you have two events A, B, and there's an intersection A intersect B. And we'll assume P of A is positive, P of B is positive. This is given to you, right? So, everything starts from this A intersect B. Right. So, what is P of A intersect B? A intersect B is inside A, it is also inside B. So, it is an event which is inside both the conditional spaces, right. So, you condition on A intersect B is there, you condition on B also, A intersect B is there. So, you can write probability of A intersect B in two ways using the either of the conditional spaces. You can write P of A intersect B as probability of B times probability of A given B. You can also write it as probability of A times probability of B given A. Okay. So that's it, that's Bayes' theorem. It's very, very simple, right? You know this equality is definitely true. From here, you can write B given A in terms of probability of B, probability of A given B, and probability of A. And the relationship is given there, probability of B into probability of A given B, I mean multiplied by probability of A given B, divided by probability of A. Okay? So that's as simple as that. There's nothing majorly going on here. So it's just this A intersect B, which is in both these conditional spaces, and sort of gives you a very natural connect between probability of A intersect B and B intersect A. Now these two laws, they seem so simple, but together they can really open the door for you for so many problems. So this law of total probability and Bayes' theorem are at the heart of so many applications in probability, and we'll see them over and over and over again as we do statistics. Let's go back to our urn problem. Okay. So my event B is urn 1 is chosen, B complement is urn 2 is chosen, A is a red marble is picked, right? So I know probability of B complement, I know probability of A given B, I know probability of A given B complement. All these we have seen before. By law of total probability, you can very easily compute P of A is 6 by 30. So you see these guys are all easy to find, right? So P of B complement, A given B complement, P of A, all of them easily worked out. Now Bayes' theorem will give you the reverse, right? What is the reverse that I wanted? Probability of urn 1 given red, that's probability of B given A. It's just a direct application of Bayes' theorem, P of B into P of multiplied by P of A given B divided by P of A, plug it in, you get the answer 7 by 12. Okay, as easy as they come. It's just a very simple method, and you can just directly apply the formula to get the answer. Let's go back to our flu test. Okay, what was our flu test? The same scenario is put down here. Let's say the event B is the person has swine flu, event A is the person tests positive. So P of B is 0.01, P of B complement is 0.99, that we know ahead of time. A given B complement is known to you, right? So using this and the total law of total probability, we can compute probability of A. So notice what's going on here. This is very important. Okay, maybe the pen is good enough for me. So notice what's going on here. P of A, first thing I use, usually Bayes' theorem, whenever you use Bayes' theorem, just before that you will end up using law of total probability. Okay, so quite often it's stated in that fashion also. So P of A is P of this is just simple law of total probability, right? P of A given B times P of B plus P of A given B complement times P of B complement. Okay, I have just plugged it in here, I got P of A. So here's a situation where I have P of A, I have P of A given B, P of B. I know I can use Bayes' theorem and find P of B given A, and just plug in and look at the surprising answer. Are you surprised by this answer? 32.42. You've tested positive. Given that you've tested positive, given all these other statistics about the test, there's only a 32% chance that you actually have swine flu. Okay, think about what went wrong here. Think about what's going on here, right? So P of A, which is that you test positive, there are two ways you can test positive. You may either have swine flu and test positive, and you may not have swine flu and test positive. Look at this probability. This total probability is 0.0095. Look at this probability. What is this probability? 0.0198. Okay, that's the probability, right? These two are roughly in the ratio of 1:2, a little bit more than 1:2. So this case, which is what you're interested in, happens is about 1/3 probability, a little less than 1/3 probability. Okay, so this is the crucial thing. So what matters is the product of these two guys, and not just what individually P of A given B is. Even though individually 95% is like some 50 times 2%, once you multiply by the 0.01 and 0.99, they end up being just 1:2 ratio. Okay, so this probability ends up being very large. Okay, so this is something very interesting and instructive. I mean, so given these kind of numbers, one needs to be very, very careful, right? And look at how Bayes' theorem has helped you understand something very, very critical about tests. Okay, so something similar happens over and over again in practice. So what we're going to do next is, I think, a few more problems just to get our feet wet, to understand how to use this and how different situations this may arise. Okay, so here's another problem. Let me just quickly work this with you. Here's an MCQ, like in your quizzes. When you go to a quiz, you know, in this program, you have multiple choice questions with 4 choices, right? One of them is correct, and maybe this is a good model for most people, right? So for any question, there's a probability 3/4 that you actually know the answer, right? If you don't know, you're going to be guessing it, okay, and that's like random. You randomly pick one. So supposing the question was answered correctly, what is the conditional probability that the student actually knew the answer? Okay. So what's given here? So probability of correct given knows, okay, is actually 1, right? If you know the answer, you're going to be correct. Probability of correct given doesn't know, right? I'm writing everything in English. I'm not just to keep it very simple. This is going to be 1/4, isn't it? Okay. And probability of no is given as 3/4. So that implies first thing, probability of doesn't know is what? Is 1/4. That's it. This is a classic case of law of total probability, right? So you find probability of correct using law of total probability 1 times 3/4 plus 1/4 times 1/4. So that's 3/4 plus 1/16. That's 13/16, isn't it? So you know probability of correct given knows, probability of knows. You can find probability of knows given correct. Okay. So I wrote all those things in gory detail. So usually, you know, you can just directly write the answer. Once you get used to these kind of problems, you know exactly how to do this. So this would be probability of knows times probability of correct given knows divided by probability of correct. So that will work out to 3/4 times 1 divided by 13/16. That works out as 12/13. Okay, so you can see that's about 12:1 ratio. Okay, so that's good. The probability that you knew, given that you got the answer right, was overwhelming. It's very large probability. So you can see how these things work out in quite a simple way, right? Given probability of some events, you can just use the results of all that you know to move towards the probability that you want. Okay, so here's a slightly more complicated situation. Maybe the computations are going to be a bit more painful. Okay, so let's look at this. There are 2 steps. Once again, you roll a fair die. You may get an answer from 1 to 6. Then you toss as many fair coins as the number that showed on the die. Okay, so the number may show 2. You'll toss 2 fair coins, and you count the number of heads you got. Like that's one reasonable outcome. So given that 5 heads are obtained, what's the probability that the die showed 5? Okay, so once again, this is not too difficult to show. So probability of 1 and 2 and 3 and 4 and 5 and 6, all of these guys is 1/6, right? Okay, so this is your partition. What the die showed is your partition, 1 or 2 or 3 or 4 or 5 or 6, right? So that's your partition. And probability of 5 heads given that the die showed I, first thing I'm going to say is 0 if I equals 1, 2, 3, 4, right? So if the die showed only 4 and you tossed the coin, you tossed only 4 coins, there's no way you're going to see 5 heads, right? So that's not possible. So probability of 5 heads given die showed 5. So, this you can do. So, if the die showed 5, you are going to toss 5 coins. There are 32 possibilities for heads and tails, and only one of them is favorable to you, which is 5 heads. So, it is 1 by 32. Okay. So, this is a uniform distribution calculation. Okay. So, you just count the favorable outcomes among the 32 possibilities and you will get the answer. So, what about the next one? Probability of 5 heads given die showed 6. Okay. So, here again you have 64 possibilities, and if you have to have 5 heads, you have to have exactly one tail, and that one tail can happen in the first coin, second coin, third coin, fourth coin, fifth coin, sixth coin. Okay. So, you have 6 different outcomes where you can have 5 heads. So, it is 6 by 64 or 3 by 32. Okay. So, you have this complex thing that you are trying to find. You have done your partitioning. So, now I am ready to find probability of heads. So, all these I equals 1 to 4 cases will go away, only these two remain. So, I have 1 by 6, which is probability of 5 times 1 by 32 plus again a 1 by 6 times 3 by 32. 32 times 6 is 192. You have 1 plus 4, which is 1 plus 3, which is 4, 4 by 192, and that would be 1 by 48. Okay, so that is the probability of heads, 5 heads, I am sorry, 5 heads. Okay. So, now you have probability of 5 heads, your probability of 5 heads given die showed 5, probability of 5 heads given die showed 6. You do not have to bother about these other things strictly, but anyway we should be careful about it. So, how do you find the other probability? So, what is the base probability? Probability that conditional probability that the die showed 5 given 5 heads, right. This is what you have to do. So, that is going to be probability of 5 heads given die showed 5 times probability of 5 divided by probability of 5 heads. So, that is going to be 1 by 6 times 1 by 32 divided by 1 by 48, or yeah, that is okay, we can keep it like that. So, that should end up being 1 by 4, I think. Yeah. Okay, so, it is 1 by 4. Okay. So, it is just a basic calculation. You see how the same idea is used over and over again, except the computations might be a bit different and tricky at some places, but the idea is the same. You go in one direction, use the law of total probability, and then you sort of reverse and you use Bayes' theorem. Okay. So, that is the last example I am doing for Bayes' theorem. Hopefully, these two, the previous 2 lectures give you a good sample of how we can move from one conditioning to the other, do multiple conditionings, use the partitioning very smartly, and keep computing probabilities for more and more interesting events, and then in particular reverse the conditioning and use Bayes' theorem and use and find some very interesting conditional probabilities. Okay, that is the end of this lecture. Thank you.